Hello and welcome back. So in the previous segment we were talking about emission spectrums. So that was when energy was given to the atom, the electrons jumped up in their energy levels. When they came back down, they emitted energy in the form of light. And so that's an emission spectrum. But it turns out that there are two other kinds of spectrums that are also important to the astronomer. So let's first talk about the continuous spectrum. And so I'm going to be referring you to the picture that is over here. And the first thing is, let's imagine that you've got a light bulb. And so this light bulb is going to represent a black body, which means that it gives off all sorts of different kinds of light. Gives off a continuous spectrum of light. Now if you look at that, it's going to be the color white. However, let's pretend that you put your a diffraction grating over here. Remember what the diffraction grating was. Okay, and then let's pretend that your eyeball is over here, so that you're looking at the light bulb through the diffraction grating. You're going to see all the colors in that light bulb. And so you're going to see a continuous spectrum of light. You'll see all the colors of the rainbow if you do it that way. And so if you'll notice in the picture off to my left there, you'll see that it makes the brightness of those colors makes a hump. Okay, did you notice that? So going this way was the brightness, and then going this way was the wavelength, and then it was making something that looks like this as far as the brightness was concerned. So one of the colors of the rainbow, in that one it kind of looks like orange, is the brightest color that you would see through your diffraction grating. Well, that's a black body spectrum. So this thing here was a black body spectrum, so that when you are looking directly at a luminous object, and then you're looking at it through your diffraction grating, you're going to see all the colors of the rainbow, and one of those colors is going to be the brightest because you're looking at a black body curve of that object. All right, so now let's pretend that here's our light bulb here, and what we're going to do is, let's say that this is a cloud of a particular gas. So some of this light is going to hit the atoms and excite them if it's the right frequency. If it's the wrong frequency of light, then the light just keeps on going and it goes right through the cloud and doesn't do anything. But if the frequency is just right, it could make the electrons jump, and then when they come back down, they're going to emit light of a certain frequency, and then that light could go this way, or it could go this way, or it could go this way, or it could go that way. So the light is being scattered by the gas. Now let's pretend that we take our diffraction grating and we're going to put it down here. And then we're going to put our eye is going to be down here. So we're looking through the diffraction grating at the light that's being scattered by the cloud. And what are we going to see? The emission spectrum. So we'll only see certain colors that were scattered, absorbed by the atoms, and then re-emitted, scattered in different directions. Okay, now what about if we put our diffraction grating over here and then put our eye over here? So now what's happening is you're going to be seeing the light bulb missing the colors that were scattered. So what you're going to see is mainly the continuous spectrum, but it's going to be missing certain colors, so that's going to be black lines in that spectrum. And that is going to be the absorption spectrum. So it turns out that all three of these kinds of spectrums are important to astronomers, that they look at actually at all three of them and they get information from them. Okay, I'm going to be right back in the next segment after I have erased all of this.